Now, we have seen that to have the supersonic flow at the exit of a nozzle, we have seen through the area velocity relationship that the exit of a convergent nozzle, the maximum Mach number achieved is Mach 1. And to further increase in the Mach number, we must have a diverging passage at the exit of the nozzle. And then it becomes convergent divergent nozzle such that the throat at the minimum area location where the convergent portion and the divergent portions are meeting, that is termed as throat, the Mach number achieved as 1. And in turn, when the further diverging passage is attached, then due to which at the exit of this duct, convergent divergent duct, we are achieving the supersonic flow. But we have also seen that in this exercise, if by this design, if the boundaries of convergent and divergent ducts are straight, then at the exit, even though we are obtaining the supersonic flow, we are having a uniform flow but not unidirectional, and that will create another problem if we apply this kind of nozzle directly to our applications in jet aircrafts or jets, wherever we use the supersonic nozzle. To avoid this thing, so that we can avoid the thrust vectoring, that is the requirement of having a steady straight trajectory followed by this jet, then we must ensure that these boundaries are, rather than having straight, they must be contoured. That is obtained through method of characteristics. Now, going further, and that kind of nozzle is termed as convergent divergent nozzle in the name of the scientist D. Laval, and that is why it is also called as a Laval nozzle, D. Laval nozzle. Now, one more aspect we want to see, that from this area velocity relation, which we have obtained as dA by A is equal to m square minus 1 dV by V, we have seen when the area and velocity less than, when the Mach number is less than 1 and m is greater than 1, that is for subsonic flows and supersonic flows. What happens when we put m equal to 1? Clearly we can see for a non-dimensional dV by V, that is non-zero dV by V, that is it is not equal to 0, we are obtaining dA by equal to 0. What did it mean? What can we comment about this condition, that when dA by A for Mach 1 we are obtaining as 0, that is the fractional change in area is 0. To understand this thing, since we are only having one equation, then there is no provision of taking the second derivative. In doing so, let us apply the maxima minima first principle. What it says, that whenever the gradient, that is the slope of a curve, changes from negative to positive, in doing so, the point about which such changes occur, that would be the local minima point of that curve. Clearly we can see that when dA by A is less than 0, that is a convergent portion, something like this, and then it goes like this. If you consider about this point, then if we draw any tangent to this line, which is tangential to this, parallel to this contour, we find that the slope is negative if we draw the axis like this from the first quadrant. Moreover, when we draw the tangent in the divergent portion, we find it positive. Then essentially, mathematically we can see clearly that due to change of slope from negative to positive, there exists a local minima, and that is we call throat. Now, it means that m equal to 1, we essentially say that whenever the throat is choked, that is m equal to 1 is achieved, after that only we will be able to achieve supersonic flow in the divergent section. How to understand this physically? That why the choking, that is, in this condition we will just see that in this condition whatever the mass flow is entering in the convergent portion and passing through this throat, after a certain condition of pressure at the back side, which we call back pressure, this mass flow rate is maximum. And why it happens only at the throat? To understand at this moment physically, please see that whenever flow takes place from a convergent divergent nozzle, something like this, and you start controlling back pressure here, let us denote PB, and for a given stagnation pressure and stagnation temperature, initially when let us say there is no flow, suppose if this exit is covered by a plate, something like that, when there is no flow. However, as soon as we start decreasing the back pressure, what we see that some fresh streamlines tries to enter this passage, convergent divergent duct. However, if you keep on decreasing, more and more streamlines used to pass through and they comes out from the divergent portion. In doing this exercise, when you keep on decreasing, there comes a state where no more fresh streamlines used to pass through the duct because the minimum area location, that is throat, forbids in doing so. Clearly, since the minimum area location is forbidding any entering of any fresh streamlines, therefore, even though there would be some space in convergent as well as in divergent, so that the streamlines can accommodate, however, this minimum area location is not allowing doing so. We essentially find that in this case, whatever the mass flow rate obtained under this condition becomes maximum. That means, even further decrease of the back pressure, once the choking, the mass choking occurred at the throat, mass flow rate becomes maximum and it does not increase for a given set of P naught and T naught. That means, if you are essentially willing to increase the mass flow rate, you need to change the upstream stagnation condition. Now, let us see some important reference speeds or characteristic speeds in compressible flow design. Coming back to the important energy equation, which is for an inviscid flow, inviscid and adiabatic flow, that is H naught is equal to H plus V square by 2. Again, considering this analysis for a perfect gas, we can replace H as Cpt and Cp as gamma r upon gamma minus 1, which we have already seen in gas kinetics. Now, in doing so, what we obtained V, the velocity, as a square root of 2 gamma r upon gamma minus 1 T naught minus T. Now, let us see what happens if T equal to 0. Theoretically, when the temperature is 0, we have seen that this is the state when all the motions of the molecules are frozen. And in that case, since the molecules are not in moving, then the pressure is 0. That means you are essentially bringing a condition of vacuum, that is, your flow is dumping in the vacuum. In that condition, the speed which is obtained will become maximum. However, this is a theoretical condition, because before achieving T equal to 0, many of the real gases will liquefy. Therefore, since we can write the maximum V maximum as 2 gamma r upon gamma minus 1 T naught. This is a characteristic speed. Note that this kind of speed can be only achieved when the flow is coming out of an infinite reservoir, and it cannot be applied for our practical applications such as missiles in air, because in that condition the maximum speed is limited by the thrust available in turn the propulsion system. Secondly, if we take that instead of static temperature, if we consider the stagnation temperature, that the maximum temperature available to us for a flow domain, if we replace the static temperature by stagnation temperature, then we will get something of this form, and then the speed of sound at the stagnation temperature will be something A naught is equal to square root of gamma r T 0. This is indeed a second characteristic speed. Now, third one, let us say the flow is expanded, that is the gas flow or fluid flow is expanded up to critical state. Critical state means that state when the Mach becomes 1. Mach number 1 means the V is equal to A, and let us denote this state with asterisk, which is denoted here and here. In turn, the speed of sound becomes A star is equal to square root of gamma T star. Now, from the equation of energy which we have derived, we can write down, instead of V, we are writing V star and then square root of 2 gamma r upon gamma minus 1 T naught minus T star. And since V star and A star both are equal for this case, then we can write down 2 gamma r upon gamma minus 1 T naught minus T star is equal to gamma r T star. Solving this will lead to you the form something like this: T naught by T star is equal to gamma plus 1 by 2. Using again V star is equal to square root of gamma T star, if you replace this T star from here, that is 2 T naught upon gamma plus 1, you will obtain the velocity at the expanded through sonic up to sonic state, that is V star becomes square root of 2 gamma r upon gamma plus 1 T naught. Please make a difference that V maximum what we obtained is having 2 gamma r upon gamma minus 1, whereas when the flow is expanded to the sonic state, the difference is here same 2 gamma r and T naught, but gamma plus 1. One must be careful in this exercise, and we must aware of the difference between these two conditions. The previous condition was for T equal to 0, that is the flow is expanded to when the temperature is 0. However, here the flow is expanded with the Mach 1. Now, having these reference speeds in mind, let us see what the characteristics of the energy equation says. Again, considering the energy equation of the form H naught is equal to H plus V square by 2, what we essentially can write down immediately, that bringing this fellow this side, H naught minus H is nothing but Cp T naught minus T, which we can write down from dH is equal to Cp dt. In this exercise, what we can see here, that T naught, it gives to you Cp T naught is equal to Cpt plus V square by 2. That means if you divide Cp here, then you will get T naught equal to T plus V square by 2 Cp, and we have already obtained that this by replacing Cp as gamma r upon gamma minus 1 will give you this equation, that is the ratio of stagnation to static temperature is given by 1 plus gamma minus 1 by 2 m square. Note that though we have used the adiabatic energy equation for an adiabatic inviscid flow, the temperature obtained, the temperature relationship between static and stagnation conditions are always valid for irreversible and reversible cases both. That means since it is evolved from the energy equation, this equation is always valid for both reversible and irreversible cases, and this eases our analysis a lot. Now, let us see that what happens when different conditions applies to the energy equation, and those different forms of the energy equation and the different conditions we say kinematic forms of energy equation. Rewriting the h plus v square by 2 is equal to h naught, considering the flow is adiabatic, that is h naught is not changing. For a perfect gas, we again write v square plus 2 cpt is equal to constant. Replacing Cp with gamma r upon gamma minus 1, we find v square plus 2 gamma r upon gamma minus 1 T is equal to constant. Our objective here, since this is a original energy equation, let us investigate what are the values for this constant under different conditions. The first condition which we take, let us say the velocity is 0, that is speed is 0 here. If speed is 0, what if we put here, then it becomes, let us say, that is isentropically bringing the flow to the rest, then it becomes immediately the stagnation speed of sound A naught, and hence the first kinematic form which we have written is equal to v square plus 2 upon gamma minus 1 A square is equal to 2 upon gamma minus 1 A naught square. Now, this is for the case when the flow is brought down isentropically to the rest. Now, let us take the second case. What happens when the flow is brought down to a temperature which is 0? Again, theoretical case. In doing so, if the temperature is 0, that is here, then this term will be vanished, and then V becomes V maximum, we have already seen. Therefore, the second kinematic form of the energy equation is V square plus 2 upon gamma minus 1 A square is equal to V maximum square. Now, the third form, that again for sonic condition, that is when the Mach number is equal to 1, under this condition, what is the form of energy equation? That means V equal to A, and again denoting by asterisk, what we see here, that if V star is equal to A star, then in this, to reevaluate this constant of energy equation, put in place of V, please put A star square and then 2 by gamma minus 1 A star square. That means this gives you gamma plus 1 upon gamma minus 1 A star square. Putting back the value of the constant for sonic speed condition, in the energy equation we find V square plus 2 by gamma minus 1 A square as gamma plus 1 upon gamma minus 1 A asterisk square. This is the third form, however, this is the most useful form of the energy equation. Now, the important aspects in compressible flow or the gas dynamics, we also define along with Mach number a non-dimensional speed denoted by m star. Why it is required? Please see m, which is V by A. Now, what we see, that being this is a non-dimensional number, please note it is not directly proportional to V. Secondly, if we keep on increasing the velocity, and theoretically if we tends to infinity, the Mach number also tends to infinity. Therefore, what happens, this non-dimensional number becomes unbounded. To alleviate this problem, we defined another number or another non-dimensional speed such that m star, which is our non-dimensional speed, defined as speed of the object divided by speed of the sound under sonic condition. That means, if this is equal to again V and the speed at this sonic condition. Therefore, because here V star is again A star. Using this as a criteria m star, let us investigate further. Now, since m star we have ourselves defined V by A star, then let us slightly manipulate algebraically, and let us square both sides. M star square is equal to V square upon A star square. Now, because our interest is to bring our original Mach number, non-dimensional Mach number. So, V square upon A square multiplied in the denominator divided by and then multiply in the numerator and then A star square. What we obtained, this is a simple relationship that M star square is equal to M square A square upon A naught A asterisk square. Now, considering the third kinematic form we have just seen is V square plus 2 upon gamma minus 1 A square is equal to gamma plus 1 upon gamma minus 1 A star square. Now, if we divide this fellow on the left hand side, what we obtain something like this: V square upon A star square plus 2 upon gamma minus 1 A square upon A asterisk square is equal to gamma plus 1 upon gamma minus 1. Therefore, since this we have defined as M star square, replacing this and rewriting the equation again, M star square plus 2 upon gamma minus 1, then again you can divide and it's multiplied by V square here in this term to bring down the M star square and M square, and hence right hand side as it is you can write down. Therefore, taking out the M star square and M square as common in both the term, we are left with gamma minus 1 by 2 M square plus 1 in the numerator divided by gamma minus 1 in the denominator, and then right hand side also has gamma plus 1 upon gamma minus 1. Striking out both sides gamma minus 1, we are left with M star square is equal to gamma plus 1 by 2 M square upon 1 plus gamma minus 1 by 2 M square. Now, let us investigate the relationship which we obtained M star as a function of M. Please note that if we see the various flow designs depending upon the Mach number, we are going to obtain the following cases. What happens? You can investigate from this relationship that if M is less than 1, M star also comes less than 1. Okay. Further, if M is greater than 1, then again M star from the previous relationship one can definitely verify from this. When M is greater than 1, that is the flow is supersonic, M star also comes to be greater than 1, and then when M is equal to 1, the M star, this equation is also 1. Furthermore, if we have M equal to 0, then M star is equal to 0. So far, what we see under 0, 1, less than 1 and more than 1, both the M star and M are behaving similarly. But now there is a change. What happens? We just said that our purpose was that when M tends to infinity, it becomes unbounded. However, we were interested in removing this. Let us see whether we have achieved our objective. When in the previous equation, if you note down, if you take M square and divide, what will happen in doing this exercise? The M star asterisk square, if you are taking M square or dividing upside and downside, numerator and denominator, you are obtained with gamma plus 1 by 2 divided by 1 by M square plus gamma minus 1 by 2. Now, once M tends to infinity, clearly this fellow is giving me M star square is equal to gamma plus 1 divided by gamma minus 1. That means, under this condition, the M star is obtained as square root of gamma plus 1 upon gamma minus 1. That means, the relationship is something like this, that even though Mach number is unbounded, that is, it is tending to infinity, M star does not tend to infinity. Rather, it is going square root of gamma plus 1 upon gamma minus 1. And when we can see the value, that is, this is something gamma is equal to 1.4, then 2.4 divided by 0.4, that is equal to 6, and then m star tending to square root of 6. Then we have achieved that even though the Mach number is unbounded, the m star non-dimensional speed is not unbounded. Also, at this juncture, I want to clarify that all these analysis, these relationships which we have established are true for both reversible and irreversible cases, because every point, every relation to derive, we have started with adiabatic, inviscid, non-conducting flows, the energy equation, the application of energy equation. Therefore, all these relationships are valid for irreversible as well as reversible cases. However, point must be noted here that I am speaking only about the temperature or enthalpy. For reversible and irreversible cases, stagnation pressure as well as density, they are not behaving same, because stagnation pressure case, the pressure depends upon the losses, and loss of pressure in compressible flow is always the total or stagnation pressure. And irreversible cases, the pressure will always be lost, and in that case these relationships will not hold for the pressure relationship, and the stagnation pressure to static pressure relationship will not hold for irreversible cases, whereas the temperature is already valid, what we shown. Now, since we have covered this thing, now further moving ahead. Now, we have just said from a convergent and divergent nozzle that the throat is the point where the mass flow rate is maximum. Now, let us investigate what is that mass flow rate. Since in this analysis we are considering only one-dimensional flows in the duct, whether it is a convergent or a convergent divergent nozzle or even a diffuser. Therefore, from the continuity equation of m dot equal to rho AV is equal to constant, and considering for a perfect gas P equal to rho RT. Now, you need to realize that what we are trying to achieve from a stagnation state of P naught, T naught, rho naught, we are expanding the flow to P, rho and T, that is from stagnation to static condition, and we are willing to obtain what is the mass flow rate. That is what essentially we performed the exercise in the convergent divergent nozzle, which is being operated from a infinite reservoir, where the condition is P naught, T naught and rho naught stagnation conditions, and we are interested that along the duct what is P, rho and T, and then in turn in these parametric terms what is the mass flow rate. Therefore, let us investigate m dot equal to rho AV for a steady one-dimensional flow. If you replace rho using equation of state for a perfect gas or an ideal gas, P by RT, area times velocity. Now, we have to bring down what exactly that if I multiply gamma here upside and gamma above side, then I am trying to bring that V should be replaced with Mach number. That means a algebraic jugglery is required. Please see here that m dot by A is equal to PV upon that gamma square root of gamma RT into square root of gamma RT is nothing but gamma RT. Therefore, the gamma RT in the previous expression is being bifurcated as 2 square root, and one is used here and another is used here, and the numerator we are seeing that it was gamma, and I have written that gamma as a square root of gamma and whole square. This essentially is nothing but your gamma in the previous expression. In doing so, what immediately we obtain that this V and this is nothing but your A. V by A is replaced as Mach number, and further square root of gamma square, and then it will lead to you the square root of gamma RT, and take the square root of gamma outside, and then let the specific gas constant for the gas as well as square root of T. Now, striking off one square root of gamma with this square, leaving single square root of gamma in the numerator, and hence m dot by A will become P, take this square root of gamma this side, and square root R square root T at this location, and m is already present. Moreover, I am going to divide and multiply with square root of T naught and P naught. This is to use my isentropic relationship P naught by P and T naught by T. In doing this exercise, rather than taking T naught T here, I will include square root of T naught, which is a constant for a reservoir. That is my objective. And in place of this P, I will take up this P naught, because why I am doing this exercise is that P and T along the duct is changing. The constant thing for me for a given set of conditions is P naught and T naught. That is why rewriting this equation of this form, P naught m square root of gamma divided by square root of RT naught multiplied by square root of T naught divided by this T, and hence gives this expression. Then again multiply by 1 by P naught by P. Now clearly I can replace this P naught by P and T naught by T with isentropic relationship, and in doing so I can obtain the final expression of something like this: m dot by A is equal to P naught square root of gamma upon square root of RT naught m in the bracket 1 plus gamma minus 1 by 2 m square to the power minus gamma plus 1 upon 2 gamma minus 1. Now, this is the mass flow rate inside a duct for a given set of stagnation conditions P naught and T naught. Let us see mathematically what it gives the maximum mass flow rate when it gives. To maximize the mass flow rate, considering this as a whole function, let us take the differentiation with respect to Mach number, because the Mach number is a parameter which is changing here. In doing so, let us take the first derivative of this m dot by A is equal to 0, and we will immediately lead to the Mach number 1 as the condition. Now, taking again the differentiation which has been shown here and introducing the value of m equal to 1, what we achieve that the second derivative of m dot by A is nothing but negative. We know from again the maxima minima second principle that wherefore the first derivative value, if the second derivative comes out to be negative, obviously the function have a local maximum. Therefore, for m equal to 1, that is along the duct wherever the Mach number is 1, under that condition the mass flow rate becomes maximum. And eventually in a convergent divergent nozzle, we have seen that the minimum area location is nothing but the throat, and this is why that Mach number 1, as soon as throat has the Mach number 1, it becomes choked. That means the mass flow rate becomes maximum. And I hope that from our physical discussion, physical explanation, as well as this mathematical exercise, the audience can appreciate both mathematically and physically that why in the convergent divergent nozzle, why a supersonic flow is always achieved at the exit, under what condition, and why this is in accordance, the mathematical derivations are in accordance with the physical explanation, that is the physics behind the flow. Now, moving on further, if we replace A under this condition, what we have just obtained that under m equal to 1, since the area here becomes the throat area, and throat area that too becomes under m equal to 1 choking condition. The throat area is generally in a convergent divergent nozzle is represented as AT, But when the Mach number has become 1, then this is represented again as a critical state, and hence it is represented as A star. If we replace A with A star for m equal to 1, we obtain the maximum mass flow rate expression is like this. What we observe, the maximum mass flow rate is directly proportional to P naught upon square root of T naught. This again a simple mathematical result gives information which we said while defining the physics behind this flow, that if you want to increase the maximum mass flow rate, you need to change the entry condition, that is the reservoir condition, P naught and T naught. Otherwise, despite decreasing the back pressure further, the mass flow rate for a given set of reservoir condition will not change. Further, let us move that we have obtained the general mass flow rate per unit area expression is something like this. However, when the maximum mass flow rate result what we obtained is something like this. Now, if you divide these two simple mathematical exercise will give you a very peculiar relationship termed as area Mach number relationship. Now, in doing so, let us divide Mach number, the second equation, that is m dot by A star divided by m dot by A. This gives you inherently A by A star and something right hand side. That expression while doing mathematical exercise here give you such a broad expression something like this. And solving this expression, the final expression we must remember that A by A star is equal to 1 by m, 2 by gamma plus 1, 1 plus gamma minus 1 by 2 m square to the power gamma plus 1 upon 2 gamma minus 1. Though it is a big expression, but it deals a very fantastic, it leads to fantastic results. Let us plot this result. I have plotted for you here this curve A by A star with respect to the Mach number. The behavior is something like this, which is shown with the black line. What is, you can see that if you consider a straight line, considering that is less for the same A by A star, if you draw a straight line something like this, which I have drawn here, then this straight line is going to cut the curve at 2 points. If you draw the vertical line that is trying to obtain for this particular case, let us say this is M1, and for this case this is M2. Now, with the minimum, when A is A star, we know that this is the Mach number is 1. So, it means this is the case which we must understand here, which is very much important from a convergent divergent nozzle point of view. That means for same area ratio, the area Mach number relationship gives me two values of Mach number. One comes subsonic and other comes supersonic. And this is why in a convergent divergent nozzle, let us look back again, is that for same area ratio of A by A star, the Mach number essentially in a convergent portion is subsonic, whereas in the divergent portion it is supersonic, with a condition that your throat A star is choked. Based on this principle only, the convergent divergent nozzles are designed. One must remember and keep this fact in mind. Moreover, this A by A star from this graph immediately draws an attention that it is always more than 1. That means A by A star is the value of A by A star is always greater than 1. Now, moving ahead and extending our discussion. Whenever fluid flows in a duct, whether incompressible or a compressible, from Newton's action-reaction principle, whatever the fluid applies the force while moving the duct or a passage, this equal reaction occurs from the duct as well. In compressible flows, this is given by an important function known as impulse function, and it says that while any compressible flows through a duct, the term P into A, that is the pressure into area, and m dot into V, that is the momentum, when rate of momentum is given as a important function like f. That means if f is equal to Pa plus m dot V, and then we can write down by taking P as a common, and then we can write down essentially and replacing m dot as rho A V, we can write down immediately 1 plus rho V square upon P. And again, rho V square is given as replaced with 1 by 2 rho V square. It can be replaced as, for a compressible flow situation, gamma P m square, which we have already seen. If you replace rho V square striking out 2 both sides, then I can write down immediately Pa 1 plus gamma m square. This is a very important function known as impulse function for compressible flow. Moving ahead, for when this is obtained for a general m, for obtaining the value for m equal to 1, that is critical state, let us again conventionally write down f as f star. That is what I have done here, that for m equal to 1, f becomes f star, and hence again the properties like P star, A star, 1 plus gamma. Let us divide f by f star, P by P, then it becomes right hand side P by P star, A by A star, 1 plus gamma m square upon 1 plus gamma. Since we are aware of the relationship of P by P naught, then by doing this exercise, that is P by P naught multiplied by P naught divided by P star and A by A star, and in the bracket 1 plus gamma m square divided by 1 plus gamma. Please note that in compressible flow fluid mechanics, one dimensional flow, this f by f star, which is basically written as P by P naught by P star, A by A star, 1 plus gamma m square, 1 plus gamma. In doing this exercise, there are 3 possibilities of incurring the change in compressible flow. One is that you are having the inviscid flow while there is no heat transfer, or obviously there is no friction as well. That means you are incorporating area change to change the state of the flow. Moreover, you can also do this exercise that you are not allowing the area change, that is your passage or duct is of having the constant area, but you are allowing only the friction to cause the change of a state of a compressible flow. Finally, there may be a condition that you still have a constant area duct, but you do not have the friction, that is you have a frictionless flow while you are allowing the heat transfer to change the state of this compressible flow. That means to change the state of a compressible flow, there are 3 possibilities, that is the area variation, without friction, without heat transfer, with friction in a constant area passage, without heat transfer, and this type of flow is termed as Fano flow, that is flow with friction, named after their inventor. Thirdly, in the constant area passage with the heat transfer but without friction, these kind of flows are termed Rayleigh flow, again named after their inventor. That means if we look back f by f star, these driving potentials, that is P by P naught by P star, A by A star, and this is same for everywhere case, this must be replaced according to the flow under investigation out of these 3 which I have discussed. Please note that in real situation, all the three, that is there will be area change, frictions will always be present in the real scenario, and heat transfer may be also present. That means in the real situation, these three cases to occur the change of state of the flow from one state to another state are always possible. However, for simplification only, in the gas dynamics at undergraduate level, you are being taught that area relationship, that is the area change without friction and heat transfer, and Fano flow and Rayleigh flow are studied differently. However, in the advanced courses, when you move on and when you perform the research in this area, then all of them must be studied together. And that lead to very complex governing equation which is difficult to analyze. That means in our case here at the undergraduate course, what we see here, that we must tell to the students that this is a general case. However, we have just found our relationship of P by P naught by P star, and area relationship, area Mach number relationship for area variation without friction, without heat transfer, that is inviscid flow without inviscid and adiabatic flow. Then if we replace those relationships here, that is isentropic flow, reversible and adiabatic with area change and frictionless, that is inviscid flow, then P by P naught, then we can write down it's like this: when m is equal to 1, this essentially becomes P naught by P star, and hence area Mach number relationship we have just obtained. Introducing these three relationships in the previous f by f star, the impulse function, we will obtain the equation something like this: f by f star 1 plus gamma m square upon m times 2 into gamma plus 1, 1 plus gamma minus 1 by 2 m square to the power 1 by 2. This relationship is applicable to a steady one-dimensional isentropic flow with inviscid flow conditions. And please note that in the any gas dynamics book, you will find that against the Mach number along with area variation and the properties like P by P naught, T by T naught, rho by rho naught, that is static to stagnation conditions, you are also given with f by f star just to so that you can obtain the change in momentum from this impulse function when the compressible fluid flows takes place. Now, another important, very important fact which I want to discuss it here. From the fluid mechanics courses, we are continuously applying and deriving the equation, famous equation, Bernoulli's equation, and we are aware of that the Bernoulli's equation is given for an incompressible flow is P plus half rho V square is equal to constant, subject to the condition that we are ignoring the potential energy term. In doing so, we can see here the P refers to the pressure forces and half rho V square essentially is the inertial forces. That means if we apply this thing from this equation, if the constant is P naught, we also have seen that P naught minus this static pressure P is essentially gives me a dynamic pressure which is given as this term, that is half rho V square for incompressible flow. But please understand that this equation have been derived by the famous inviscid flow momentum equation, that is termed as dP by rho plus V dV, that is nothing but your Euler's equation. However, in an incompressible flow, when temperature effects are ignored, the conditions are almost approximated as isothermal. Whereas in compressible flow situation, we are keep discussing that the kinetic energy is very high than the heat content of the flow medium. Therefore, slight increase in kinetic energy or variation in the kinetic energy leads to a large difference between static and stagnation condition. That means what could be the form? That means this Bernoulli's equation form is essentially not valid for a compressible flow. Then what could be that form? There are basically two ways to obtain this thing. One way is that from the Euler's equation, the governing equation, we immediately say that since this is no more isothermal case, if compressible flow equation between the pressure and density of the form is equal to constant is used, then whatever the equation we will achieve immediately is the compressible form of the Bernoulli's equation. Let us investigate that, taking again the Euler equation in absence of body forces. For an isentropic flow, as I said, P by rho to the power gamma is equal to constant I have written here. Now taking the logarithmic of this term both sides and take the derivative, then it leads to dP by P plus gamma d rho by rho is equal to 0 from ln P gamma ln rho is equal to constant. Further, please note that here this should be minus, because this P by ln P minus gamma ln rho is equal to constant, which is again the logarithmic of this constant phi further a. If this is given as k, let us say this is k1. Then taking the derivative, we will obtain dP by P minus gamma d rho by rho is equal to 0. That means taking this term at the right hand side, I will obtain dP is equal to gamma P d rho by rho, which can be further used as P by rho to the power gamma as k. Introducing k, I can write down rho to the power gamma minus 1 d rho just to remove P. Further, if we integrate this equation further, I will obtain gamma P d rho by rho square plus V square by 2 is equal to constant. Further, gamma P rho to the power minus 2 d rho, I am rewriting this equation, and since we have introduced P by rho to the power gamma is equal to k here, I can obtain directly from here these terms, that is gamma rho to the power gamma minus 1, because the gamma minus 2, and it will lead to you the small integration x to the power n dx is nothing but x to the power n plus 1 upon n plus 1. And in this case, what we see here, that is gamma minus 1 gamma minus 2 is nothing but your n here. Hence, rho to the power gamma minus 1 upon gamma minus 1 plus V square by 2 is equal to constant. And further, what we see that gamma upon gamma minus 1, we can write down this P by further rho to the power gamma minus 1 is used again P by rho to the power gamma n is equal to constant. I can write down this term, that is gamma upon gamma minus 1 P by rho plus V square by 2 is equal to constant. That means to evaluate this constant, if the velocity is 0, then we will have the stagnation condition P as P naught and rho as rho naught. That means I will evaluate the constant gamma upon gamma minus 1 P naught by rho naught, and hence finally we will obtain the equation, that is putting back the value of constant which I have obtained here in this above equation. That will lead to me gamma upon gamma minus 1 P by rho plus V square by 2 is equal to gamma upon gamma minus 1 P naught by rho naught. This is a famous compressible form of Bernoulli's equation. This can also be achieved through your immediately H naught is equal to H plus V square by 2. If you can use here, that is Cp T naught is equal to Cpt plus V square by 2, and again taking gamma r T naught and gamma minus 1 is equal to gamma r T upon gamma minus 1 plus V square by 2, and introducing the equation of state, we can write down this equation directly. P naught by, that is P naught equal to rho r T naught and P equal to rho r T. That will again lead to the same equation. So whatever the way you adopt, you will find the equation of this form, which is known as compressible form of the Bernoulli's equation. Now let us see the one more topic, that is the pressure coefficient. Please note that in the aerodynamics, low speed aerodynamics and the fluid mechanics, we define the pressure coefficient is something like Cp P minus P infinity upon Q infinity. That means we can replace the Q infinity where infinity represents the free stream conditions. That means if the model, something, let's say a sphere is kept in the uniform flow, then it means the flow is approaching here, and then any local pressure here P, and if the condition is P infinity here, then P minus P infinity upon the dynamic pressure, that is here V infinity, is represented as in the form of Cp. However, please note that the compressible dynamic pressure is always more than incompressible dynamic pressure. Doing similar exercise, because the pressure coefficient is that change the local pressure difference with respect to the free stream and divided by dynamic pressure is defined as pressure coefficient. By definition, we can write down for the compressible flow, the Cp for compressible flow is as P minus P infinity, that is the local change in pressure, divided by P naught minus P infinity, which again gives me a dynamic pressure in terms of for the compressible flow. However, conventionally in the gas dynamics, it is adopted that the Cp is, even though not 100% correct, but is defined as the previous equation, that is Cp is equal to P minus P infinity upon Q infinity. In this case, we can write down P minus P infinity again, taking the same. However, here 1 by rho V infinity square is changed as 1 by 2 gamma P infinity square M infinity square. Again, doing this P by P infinity minus 1 2 by gamma infinity square, I am going to algebraically manipulate and divide by P naught and P naught here, so that I can replace P by P naught and P naught by P infinity. That means these two relationships with a single m at local Mach number over the body as well as the free stream Mach number, this relationship. Introducing that relationship in the Cp definition, I can get 2 by gamma infinity square, 2 plus gamma minus 1 m infinity square upon 2 plus gamma minus 1 m square to the power gamma upon gamma minus 1 minus 1. And now using the energy equation, that is H naught is equal to H plus V square by 2 over the body for a compressible flow somewhere here and somewhere here. Then applying this equation and this equation, I will obtain such a big expression that is termed as pressure coefficient for the compressible flow medium.